Let's explore the equations that define Snell's law. You may have noticed that when you place an object in a glass of water, that the submerged portion under the water and the portion that extends out into the air don't quite line up. The object looks bent because the light bends as it passes from one medium to the other. This is a property of all waves called refraction. We can define refraction as the change in direction of a wave passing from one medium to another caused by its change in speed. Now, as it refracts, it also reflects. Notice it reflects off. It also changes direction, speed, and wavelength. When it reflects, we notice angle of incidence equals angle of reflection. We see the same speed. It reflects in the same medium. However, when it refracts, it changes direction, it changes speed, and it refracts into a new medium. You can observe refraction in water waves. As the wave moves from a shallow to deep medium, it speeds up. As it speeds up, the wavelength moves up or increases. The angle of refraction increases or bends away from the normal line. In other words,
Up and away!
The index of refraction is essential to understanding Snell's law. It determines how fast light travels through a medium. The speed of light in a vacuum divided by the speed of light in that medium gives you the index of refraction. More mathematically, we can state that n, the index of refraction, equals c, the speed of light, which is 3 times 10 to the 8th, divided by whatever speed light travels through that medium. Using this formula, we can find the index of refraction if light travels at 1.81 times 10 to the 8th meters per second through a medium. So we know the speed of light in a vacuum is c, 3 times 10 to the 8th meters per second. The velocity in this particular medium is 1.81 times 10 to the meters per second. We're looking for n, the index of refraction. We know the ratio is c, the speed of light, divided by v, the velocity of light traveling through that medium. Substitute in what you know. This is where your calculator comes in handy. 3 8 divided by 1.81 8 gives us 1.66. Now, if we look at this chart of index or indices of refraction, we see that 1.66 is not just glass, but more specifically, flint glass's index of refraction. If you use the same simulation, you can examine the relationship between the sine of the angle of incidence, or angle 1, and the angle of refraction, or angle 2, because it's the material you're going into. As light changes mediums, it refracts. The ratio between the indices of refraction of the two mediums determines this change in speed, direction, and wavelength. If you plot these two sets of values, the sine of angle 1 versus the sine of angle 2 against each other, a direct relationship forms, a nice straight line. So this linearized mathematical equation in slope-intercept form, y equals mx plus b, is represented by sine of the angle of refraction, or angle 2, equal to 0.75, our slope, times the sine of the angle of incidence, or angle 1. Using this graph and relationship, we can write an equation in slope-intercept form. If we change things around, instead of using theta r and theta I, we think of it as theta 2 and theta 1. We also can get rid of the plus 1. Instead of 0.75, we can rewrite that as the fraction rise over run of 1 divided by 0.133. Now to solve this and simplify a little bit, I'm going to multiply both sides by 1.33. I want to get it on the other side. Now both trig ratios, sine of theta 2 and sine of theta 1, each have a multiplier. They each have a coefficient in front of them. Just for numeric sake, I'm going to put them in theta 1, theta 2 order. If we reorganize that relationship in this order, we get Snell's law. N1 is the index of refraction from your starting material. Most times, this is air. This is a coefficient of 1. If we're talking about N2, this is the index of refraction of the material that light is going into. N2 into. It's the second material's index of refraction. Sine of theta 1. This is that initial or incidence ray angle relative to the normal. Theta 2 or sine of theta 2 is the angle of refraction relative to the normal. 1 is the angle that it begins with. 2 is the angle it goes into or ends with. Let's say a ray of light is traveling from ethyl alcohol, which has an index of refraction or N of 1.36 at an angle of incidence of 30 degrees. If the light has an angle of refraction of 27 degrees, what is the index of refraction of the final material or the material that light is going into? We can write out our givens. Well, we know the initial material, the starting materials, N is 1.36. We know the angle of incidence, which is theta 1, is 30 degrees. It refracts, the angle of refraction is 27 degrees, theta 2. We're looking for N2, the index of refraction of the second material, the material that we're going into, N2 into. There's our equation. We know 3 of those. We need the 4th. Remember, sine is not just a separate thing. It's part of the theta. Plug in what you know. So 1.36 times sine of theta. N2, there's our unknown, times sine of 27. I'm going to divide both sides by sine of 27. Remember, sine and the angle go together. They're connected at all times. I can plug that directly in my calculator. 1.36 times sine of theta, or sine of 30, divide by sine of 27, and I get 1.5. That means my index of refraction of the material I'm going into, my N2, represents lucite, 1.5. If you have to solve for an angle, it's more challenging. Let's say that light travels from air, which has an index of refraction of 1, into zircon, which has an index of refraction of 1.92, at an angle of incidence of 40 degrees relative to the normal. What is the angle of refraction? As always, start by listing out your givens. N1, the index of refraction of the initial starting material is 1, it's air. N2, the material that it's going into is 1.92 for its index of refraction. We know the angle of incidence, angle theta 1, is 40 degrees. We're looking for theta 2's angle. There's our formula. Substitute in what you know, and then we're going to solve for what we don't. So I'm going to divide both sides by 1.92. So in my calculator, I can simplify out that 1 and just do sine of 40 divided by 1.92. Now that gives me the sine of theta 2. I want the angle. I want to know what theta 2 is. So just like the inverse of multiplication is division, I do the inverse of sine. When I get that, I get an angle of 19.6 degrees. That's my angle of refraction. Refraction, the change in speed, wavelength, and direction, helps explain many phenomena from human vision and optics to optical illusions. These relationships and formulas help to quantify this refraction concept. You can explore and replicate refraction by placing a coin in 2 bowls and pouring water into one. The refraction of light will allow you to see one coin at a certain angle, but not the other.